record these, and they record what's on the screen and our voices, no faces. Is that green light on?
Mhm.
It is.
Mhm.
Yeah, so you guys have to help me remember to push the record button. So if everybody can keep an eye, and if that green light ever goes out, say, hey Aaron, the green light's out, because it's pretty rare, but sometimes this thing will have a blip and it'll stop recording. But given that, I just wanted, 'cause sometimes I feel like in this class, especially this first part of this class, is we dig into how to think about this stuff in terms of conservation of mass, momentum, and energy, and all the equations that we could use, and we kind of lose sight of the big picture of why we're interested in doing this stuff. And so I did want to just point out a few things that just have happened in the last year, really, just to think about what we might be doing. So this was the Nepal earthquake last year, which was pretty devastating. It was 7.8 thousand people dead. The questions, the way that we would approach this eventually is just thinking about, well, what makes strain build up in the crust and allowing it to slowly deform versus actually cracking. And that comes down to looking at the stresses in the whole area, understanding what the material properties might be, like what's that point at which something would fracture versus just oozy deform. We'll go into, Silly Putty is a great model for that. But then every material is different. We have, when there's sediments versus bedrock, the same earthquake will cause a different amount of damage. And depending, of course, on how deep it is, so there's all sorts of different things that we can look at. So what this is an INSAR satellite measurements looking at the landscape before and after and creating an interferogram in order to look at deformation of that landscape that can help us see what's going on. And so the bullseye of deformation is right there, and each one of these fringes, how many of you have seen this kind of a INSAR map before? Yeah, it's really amazing to see that. Each one of these fringes is a certain amount of deformation. In this case, it was almost all vertical deformation because it was a compressional thrust fault. And the landscape went up about a meter in this bullseye, and then it kind of spread out and was less, and you get down to near zero deformation there. There also was a localized slip of up to like 7 meters, but I think that's more horizontal. But this is the vertical deformation that happened. But how this deformation ends up feeling, how it's shaking, all of that stuff will depend on material properties as well, and what the landscape is like. There was another 7.8 just a few months ago. How many of you guys heard about this one?
Is it the one in Italy? No, of course.
No, it was in Ecuador.
Oh,
And yeah, same magnitude, but fewer people died, but still for Ecuador it was actually pretty devastating. I happened to go there, and I had I'd heard about it, but then just kind of let it go because it didn't make as much news as the Nepal earthquake. But I ended up there in June and discovered that nearly the entire town of Guayaquil was shut down. They couldn't get the schools going. They were trying to get things started, and I was staying with somebody who works for the Ministry of Education, and she was just racing around working nonstop just to try to get schools up and started for their July 1 start date that they usually have, and they managed to get things going, but the schools were all delayed by a week or two. So this one, technically the same size, it didn't have quite as much uplift, but the same kind of a thing. This was the bullseye of the deformation, and the same thing having fringes going out. And it was more like about 60 to 70 centimeters of uplift, I believe. This is a subduction zone area, and epicenter is actually out there a ways. But in this class, we will get a little bit into the fracturing part. We'll talk much more about the deformation that might lead up to the actual fracturing. And so what's happening as the plates go down, as things get pushed around, when you take a material like silly putty and you're just stretching it slowly, there is that point, if you go fast enough, that apparently not, there we go. If you go fast enough that you can get fracturing to happen. So the material properties end up playing a really important role in a lot of what we do. And so it's good to just keep in mind
So
that there's real applications.
the difference is the time it took to release that energy is different between the two events.
Well, the depth that it happens,
Oh, the depth,
yeah, the depth that it happens, so you can also create a shake map, which is different. That's what actually is felt on the surface. But yeah, the magnitude 7.8 doesn't necessarily tell you if you're going to have the same amount of depth or the same amount of motion or shaking. It is a description of the energy released, but how that energy released interacts with the surrounding rock.
And
is
never of
what's
time.
different.
It's never it's not a function of time either, right? Assuming that's all released at that box of time, and that is a second or whatever.
Yeah.
Or it could be a minute, I guess.
Well, yeah, so bigger ones are longer. They do, the magnitude often does have some relation, it's not a linear relationship to the amount of time. Like if it's shaking, if you're sitting there and you feel even a faint earthquake, but it lasts a long time, you know that was a big one that's far away. Versus if you feel a little bit of shaking and it was just really short, then it's probably a nearby one that's a lower magnitude.
But they'll add all those joules in that minute into so I mean, so I guess what I'm saying, those different intensity, those different numbers actually represent different time boxes that they integrated over.
Yeah, yeah, it's an integrated total energy, yeah.
Which is different. Each time box is different. They're not
It could
all
be
50 seconds or all 6. I mean, they're
right, right. That's what. Yeah. So generally, bigger magnitude are longer, but there's not. Yeah, it's not all an exact relationship between. Because like some of the deep tsunami generating ones might be slower evolving earthquakes that spread out energy a little bit differently. But the properties of the surface rock and then the properties of the rock right underneath it also end up because of fracture at the surface. And this is where a Seeker's bar can be a great model. And we'll play with these a little bit more. But a fracture at the surface of an earthquake does not necessarily mean that it's fracturing all the way down deep. So the crustal materials, there'll be a variation in how the properties evolve, how the properties change with depth. So when you do have an earthquake, you see the crack at the surface. It's not cracked all the way through. Obviously, there has to be. It gets to the center of the earth if you cracked it all the way through. So there'll be a change in the properties as you go down, and a change in the amount of stress and strain as a function of depth and space. And so getting a handle on these kind of, where are the stresses highest, where then it's the material property. You can take the same amount of force and apply it to a Snickers bar and an Almond Joy, and you'll get a different amount of movement in your candy bar. So the stress itself does not necessarily tell you how it's going to behave. The stress with the material properties tells you what the deformation is going to be. And in this class, we'll use deformation is probably the word that you hear most often, just how something deforms. But strain is then the word that we use that helps helps quantify it. There are subtle differences between the two, but the general term is deformation. So it's a connection of knowing what the stresses and strains, what the stresses are, and then how that plays out depends on the material properties. And we'll get into that in a lot more detail. But then there's other things that come in different ways. So this is also in Ecuador. They've been having multiple issues. This is the Cotopaxi volcano, which is right near Quito, the big city with millions of people. So they've been very on edge watching this volcano erupt. It seems like it's calmed down now. As of yesterday, the last I heard was that it was relatively calm. But this started last year and has been going on at least until February or so. But there's a lot going on with this that we can think about in this same idea. This is data from one GPS station on the flank of the volcano, and this is the beginning of 2014, the beginning of 2015, and then this is the beginning of 2016. And this one GPS pole was moving along steadily, doing just the normal background movement of the whole area, and then you can see that it suddenly was pushed more westward in this case, because this is the east-west component of that station. So you have this big background, just movement of the whole area, and then once the volcano started changing, evolving, the magma started moving within it, you can see that it changed the direction that it's moving. I couldn't find a similar INSAR map of this volcano. I don't know that anybody has at least nobody has done it and put it up on Google yet, because there actually were a bunch of talks at the EGU conference in Vienna this spring about this eruption. So I think that there's going to be some papers coming out about it, but not yet. But again, we can take information like this and think about conservation of mass, conservation of momentum, which is how the stress is distributed and moving through, and conservation of energy, and to try to understand what might be happening here. And here we have different material properties. We might have material properties of lava, we might have pyroclastic flows, and even the gas clouds. A lot of the concepts that we're covering, we're mostly going to be talking about solids in this class, but the underlying concepts apply to atmosphere and ocean movement too. So the underlying concepts are all there. And then this was just published in the New York Times a few days ago. Did anybody see this article about sea level rising and how it's affecting the coastal cities of the U.S.? And so this is Charleston, South Carolina, a picture from there. And basically every time there's a pretty high tide, it starts to flood the streets now. And this is going on in a bunch of different cities. There's been these, it doesn't have to be a rainy day to get flooding. They call it sunny day flooding on all of these coastal towns all over the eastern seaboard. But this also can be looked at as a problem in using these same geophysical concepts. In this case, the relative sea level rise in these areas is a combination of the eustatic sea level rise, which is the actual volume change in the ocean, which in this case mostly comes from expansion, thermal expansion of the water itself, along with melting glaciers. Those are the two biggest components of the eustatic sea level rise. But it turns out in a lot of these areas, in Chesapeake Bay, In particular, they've got subsidence of that area due to groundwater pumping. So we've got a conservation of mass problem where we're sucking water out of the ground that's causing subsidence. There's also remnant subsidence due to glacial isostatic rebound. So this area is still changing from the end of the last ice age a little bit. Were there glaciers here in the last ice age? Virginia? No, there weren't. But what turns out is if you put a giant ice sheet on Canada, and then you take that ice sheet off, Canada starts rebounding, right? But the whole plate is connected. So if you start rebounding here, you're actually going to have a secondary effect of having some subsidence on the other side. So it's just like if you push down on a material, you'll get a little bit of an uplift around the edges of where you push down, and so then when you pull up on it, that stuff has to rebound directly. So there's still remnants of this. The Mississippi Delta is also still has bits of remnants of change from the isostatic rebound. I don't know how much it's moving today, but the whole flow of because the Mississippi River starts up where the glaciers were and it ends where there definitely were no glaciers. And so if you think about that action that has changed the entire flow of the Mississippi River over the last 10,000 years, when you took that glacier away and you're changing the whole landscape.
So eustatic includes both the volume change and temperature change of the water, which also increases volume.
Yeah.
So both of those components are inside.
Well,
that
it's sort
definition.
of eustatic is the total volume change from all sources.
Oh, I see. Okay.
It's just you have to take the eustatic sea level rise and apply it locally.
Right.
So if you don't know what local.
It's
sea
not
level,
just conservation of
sorry,
mass.
I should have said this should be local sea level rise, not relative. Local sea level rise, which is relative for that place.
Sure. Okay.
So these are local effects. This is kind of the global effect. So depending on where you are and what's going on. So for example, down in Gustavus, Alaska, Glacier Bay National Park, there we did have a glacier. We took the glacier away in 1960, or before that, the last 100 years, it's been shrinking. That whole area is rising. So even though eustatic sea level is going up, they're actually seeing local sea level drop pretty substantially because the earth is rising back up. So the tidal flats are all rising up out of the water at a pretty fast rate still right now because that response. And Jeff's going to get a lot more into the glacial isostatic rebound specifics later in the class.
I'm curious, what's a fast rate for that? Ballpark
Good
figure.
question. Like, noticeable by the people who live there. So centimeters a year.
Okay. Oh wow.
Probably. I don't know off the top of my head exactly, but something that's noticeable to just people who live there. Okay. Oh. Have you guys seen this? If not, it's
Oh,
really
I love this
Yeah.
website.
Yeah, I love it too. This is the jet stream. Alaska's right here. Probably can't see very well. We're right there in this little. Looks like we're in a little lull right now. Even though this is all atmospheric stuff, there are complexities with air which is compressible that we're mostly not going to deal with in this class. So we're mostly going to assume that things aren't compressible because it does make the math one level more complicated. But the concepts all still apply in terms of, water flowing in a river. This is air, but the same ideas apply to water, which is incompressible. So that we will do in this class. But just the patterns that you get eddies forming, motion patterns, all of these things fit within the same ideas of what we're going to be looking at in terms of conservation of mass, conservation of momentum, and conservation of energy. And all of this stuff fits in there because the whole reason that the Gulf Stream is there and the heat that has trying to get transported from equator up to the poles, there's a bunch of conservation of energy concepts in our atmospheric circulation. There's conservation of momentum in there, and conservation of mass. And we'll get into some more details about what you can get out of this. But in general, you bring all three of those equations together with the properties. In this case, it's air. Some kind of air, some with moisture, some with not. So you've got variable changing moisture, but there's a lot. These are basically what we're digging into is the fundamentals that would describe this as well. So ocean circulation is similar in the sense that it moves around according, all of it is according to those same three laws. Oops. So basically, really, just what I wanted to say is, we can't necessarily stop earthquakes from happening, the volcanoes from going off, or all of this stuff, but we can, as geophysicists, start to provide some assistance of helping understand them, maybe figuring out how to mitigate problems, trying to warn people. You can see volcanoes change before they erupt usually. So even though you can't pick the certain date, the reason that nobody died in the Mount St. Helens eruption, or 2 people died in the Mount St. Helens eruption in 1980, was because they were paying attention and they could see that it was happening and they evacuated a bunch of people. The same with Ecuador. I don't think anybody died in that eruption. They did evacuate thousands, tens of thousands of people from the local area. So it's just nice to remember this, and just to keep kind of that big picture in your head in this class. So, any questions on that stuff? It's just kind of a little introduction, storytelling introduction. But so what we're going to dig into today is the idea of how we take these conservation laws, which you've heard now, mass, momentum, and energy. How do we start to think about them in order to get at some of these problems? In this whole field of math, really is called continuum mechanics, and that's because we treat, in this particular class, we will treat all of these ideas as a continuum. And a continuum is, sometimes it's very much an idealization. We're taking, some things look like a continuum, they're smooth, they go through, there's no big gaps. You're not gonna, if you stretch this, it's not gonna necessarily form bubbles in between. It might change its boundary, but it's not gonna, you're not gonna have weird discontinuities or gaps in your mathematical equations. So we're gonna always assume that things are smooth and continuous, because that can help us be able to simplify the math down to what's doable. So the best example, if you were able to get the notes, if you haven't been on Blackboard, maybe you haven't seen the notes yet, but kind of the simplest example of a continuum is the tree versus a forest analogy. So we can study one individual tree, but if we wanted to study the whole forest, our choice could be to think about every tree individually, which would be a lot of complicated thinking if we have if we need to come up with a way to describe every single tree within that forest. that would get complicated really quickly as you go bigger and bigger in the area. So we might look for ways to simplify that. So instead of thinking about the forest as containing 5,000 different trees, we might think of the forest as a uniform, a smoothly varying material that's got 20% spruce trees in this one corner, and then that kind of evolves to where you have 50% birch on this area, and we might start to put, just like in around Fairbanks, you might start to put relationships to knowing, well, at these elevations on the landscape, we have forests that have 80% birch trees, and coming up with various ways of approximating where you don't have to count every single tree. You'll then define these more bulk properties in order to be able to do that. If you go in and somebody asks you to come and look at their 1 acre property, then you're going to get down to a level where you thinking that there's 80% birch trees and 10% white spruce or whatever it is, that may no longer be a good way to describe it, because now you're down to, is this particular tree going to, are the roots from this particular tree going to harm the house or the driveway that they want to put in? So there's a point at which you can't use the continuum model anymore, and it depends on the question that you're asking. Does that make sense? So I think what I'd like to do is just give you guys, or we can just do it as a group, but come up with some examples that you can think of where we might think of something from a continuum at one perspective, but then in a different time frame, in a different spatial frame, in a different just a different type of question, we might see it from a different perspective. The other one that I do put in the notes is actually a glacier, where if we're asking a question about the glacier as a whole, then we can just think of it as all pretty much ice. But if we get down to a mid-level scale, then we might have to think about it as ice with a bunch of crevasses in it, which might behave differently than ice without a bunch of crevasses in it. So there's this property change at that level. And then we get down even smaller, and we might be dealing with looking at individual ice crystals and interactions between ice crystals. And so in that case, you may or may not be able to describe certain properties at certain spatial scales according to a continuum or not. Like, you might be able to parameterize a bunch of a crevasse field as a change in the density of the ice, for example. But you might get down to a scale where you do need to care about each individual crevasse. So that's another example in there. So what can you guys do? Let's take 60 seconds silence and just think for yourself, and then we'll start throwing out some ideas.
Basically, or time or space, or both.
Sometimes it could be either, yeah. Either or both. Yeah. Any ideas you guys have?
So, like would. So you're talking about if we look at I was thinking, what about a mid-ocean ridge kind of thing, like the big picture? You just know it's spreading, but then when you take a smaller chunk, then you have these little transform faults, and then you get a smaller chunk, and then you have the tensional forces that create the smaller ridges. So are you thinking, is that what you're talking about? Like the bigger picture is?
Yeah, so in some cases, projectile subductions. So when you're at a subduction zone, you might initially, if you want to look at the really big picture, you might just treat these two plates as being a relatively similar material. You've got some mantle material down here that's got its own properties, but you're not going to deal with any details in there. You know, maybe you've got a bunch of little ocean sediments in there, but from the big picture, you're just going to forget about that stuff. Or maybe figure out a way to parameterize it or put a little, maybe some kind of a factor into your equation. You might need to account for it, but you might not. So you want to start with kind of the big picture, simple assumptions. But yeah, when you start to zoom in, you're like, okay, so this is your big picture, but what if you really want to know what's happening there? And what if you really need to understand the details of that? Then you would zoom in and you'd be like, okay, so you've got a layer of sediments on top of this, which has different properties. You've got a boundary between the two. So a continuum does not mean that you can't have a boundary, but you need to have it be continuously differentiable across that boundary. So you can have a kind of a step change in properties, but it needs to be mathematically doable. And there are ways to account for that mathematically, but usually you might have a strong gradient in a property where you hit a boundary if you want to keep it nice mathematically.
So to know, I wonder your example with snow, you can assume it's all continuous by the fact that it's mass of water just by SWE, but you can also take a look from the different thermal layers and different layers inside.
Yeah, exactly.
So that was one. Then for non-geo example, clearly quantum mechanics and light is very non-continuous.
Right, non-continuous.
Once you go down.
Yeah, if you go down to the photon level, you've got non-continuous energy packets, but on the overall level, yeah, you've got energy. So yeah, light and the photons. But yeah, with snow, you might be able to describe it, even though we know that it's ice crystals and air pockets. From that big picture, you can just describe it as having a certain density, and that density might change with depth as the air pockets get squished. So you think of it as the same substance, but with a varying density through whatever space you're looking at. But if you do need to get down to where you're thinking about meltwater percolating into the snowpack on a hot day and pooling along a wind-packed layer or something like that, then yeah, you might have to let go of that continuum and think about it differently when you get down to this level. Or you might say, well, I want to stick with my continuum model, but I'm just going to allow there to be a spike in density where I have an ice layer. So you can try to keep that continuum concept down as small as you can, because usually it ends up being mathematically easier. There's a whole suite of ways that you can mathematically model stuff using discrete element analysis, which is where, and I know there's a colleague that actually models snow as a bunch of grains. And it's because of the question that she's trying to answer, she needs to be able to do that. But it does mean that she's modeling only this tiny little bit of the snow. And if she ever wants to go bigger scale, she has to nest that smaller discrete model into a bigger continuum model. So her model might then spit out an average density over that for that little pot. But she's inside doing this whole analysis to figure out what that average density is, or whatever other property she might be interested in. But yeah, snow is a great one that has a lot of different variations. What else?
Magma chamber.
Magma chamber. So what are the different?
So if you look at it like from a deformation type view, it's looks like that, and it's just a big ball under the ground that may change. But you can get down to looking at like where different minerals are crystallizing out of it at different temperatures, how the density is changing as you go down, and then also looking into like how the shape is in reality as opposed to kind of the simplified models that get applied to it,
Yeah.
which are much
Yeah.
easier to draw.
Or easy to draw, yes. Yeah, and you could have like the concentration of different minerals, the whole composition of it might vary spatially. So you have a certain
Yeah.
composition down here, and then another composition up there, and there might be a gradual change between those two.
Mm-hmm.
And like if you have something crystallizing out that then sort of floats upward, you'll be actively evolving the composition. So you could define your composition based on, a certain percent of different minerals, and then have be a continuum property that would evolve, like a percentage of X, a percentage of B, a percentage of, all these different minerals or something. But then this doesn't, I'd probably do it a little bit differently than this, but you could define your composition in a way that you can mathematically deal with it evolving from one place to the other. On a certain scale, but then if you get down to where there's actual minerals crystallizing out and changing and moving around, then you might need to let go. But you can think of a way to describe mathematically the bulk composition. And in your very first simple model, you might say, well, let's just start out by saying that the composition is the same everywhere, and we're just going to start doing something simple with that. And we've got like a pressure going on. And then once you solve that problem, you can step it up and make it more complicated, and so let's make it a spatially variable composition. And then you do some stuff with that, and then you're like, okay, I've got this down, now I'm going to make it temporally varying, knowing that there's these processes going on with crystallization as the temperature changes. We've got all of that is doable in terms of this continuum concept. You just have to think carefully about what are those key properties that I need to keep track of.
And displaying it all in graphs.
Sorry, and
I said
displaying
displaying
it
it
all.
all in graphs.
Yeah,
So you
yeah,
have
it's-
3 dimensions. So.
It's not always easy to think of it in 3 dimensions, which is why it does. I find personally that if I can visualize the physical, the geological process going on in my head, that helps me understand what I'm seeing mathematically. So I actually really need the kind of intuitive, physical, conceptual picture in my head in order to understand what the equations are doing, or seeing how the equations are evolving. Because it helps me catch if there's something that I've done wrong in terms of mathematically describing my composition, then I can always come back to grasping that conceptual side of it. But some of you guys might be more comfortable taking the mathematical side of it and using that to generate your physical conceptual picture of it in your head. So some people are easier going that way versus this way. What else? What are some other ones?
The speed of the seismic waves for like some boundaries on the Earth, because inside the Earth, like between mantle and crustal, it has like more discontinuity, and basically it's not linear. I mean, the jump is not just jump from like mantle, the speed in the mantle and the speed in the crustal. Like there is like in the boundaries. Is something interesting is
There's a lot
happening
of weird
if
stuff
we look
happening with
closer
those boundaries.
to that point.
Yeah. Yeah, there is, boundaries can get challenging, and you do have to very carefully think about how to describe them. And sometimes, like I said, you can describe them just by having a sharp gradient, as long as it's still differentiable through that space. You can describe a boundary that way, but sometimes that just isn't good enough to answer the question you're going to answer, and then you might have to approach it from a different perspective. Cool. Any others?
I was thinking maybe like groundwater hydrology, like you know, you can sort of model how the ground is full of water at these points, or you know that it's full of this much water, and this water is coming in, this water is going out, and then maybe there's these aquifers and things. But like, if you want to, one person wants to drill a well somewhere, you have to look really like discreetly at like what's right
Yeah.
there.
Yeah, that's a good one, because groundwater, you know, we think, always when I was a kid, I thought of an aquifer as just this big bulb of water, kind of like our magma chambers.
Yeah.
But it
I still think that when you talk
obviously-
Wait, that's not how it works?
What?
Well, and then I met a real water witch who would show me where there were rivers flowing underneath us. He seemed he was a very good actor if he wasn't being real about it. Yeah, that's another one. What about some non-geology ones? I mean, you mentioned the light and photons.
Yeah, and then I was about to say more general quantum mechanics versus classical mechanics. That's exactly
Yeah, I
that
mean, quantum
difference.
mechanics by its definition, is discrete versus, yeah.
And so just light is one of them, but you can also just water flow. I'm sure you can go all the way down to the individual molecules gravitating each of them to make
Sure.
water flowing versus the actual flow.
Right, yeah, you definitely can do that. What about like something from your daily life?
I had a smoothie this morning and it was pretty continuous throughout. But if you really break it down, there's a lot of weird stuff in it.
Yes. That's awesome.
Maybe looking at like history in like if there's a big war between two countries and one of them is much bigger, much stronger, and just has a giant like army, they're probably gonna win the war eventually, but they might lose some battles along the way.
Oh.
Like that. So like in maybe the Civil War or something, you know, the North was way bigger, had a lot more people, a lot stronger economy, and all this, but they ended up losing for a long time just because the South was just winning all these battles and stuff, and so
Right. Yeah, the battle versus
like
the
it was.
war. That's a good.
About big army, but then you look at the individual soldiers in the army, like these people had more horses.
Yeah, no, that's a good one, and you could actually probably model the movement of armies, and you could probably look at that whole thing as a continual model, like the density of soldiers versus regular people, and where then you have soldiers, two different types of soldiers, and you can look at the mixing properties on the boundaries. Which
I was about to say traffic.
traffic is another one
Oh,
of my
yeah.
favorites. Yeah, traffic is a really good one, and we'll come back. We'll actually use traffic as an example of conservation of mass later on, because the cars are stuck on the road, right? You can't. So they very much abide by conservation of mass. But yeah, things get
Waves of
higher, less
traffic.
density. Waves start traveling through.
You sort of describe phase changes of traffic.
Yeah. Yeah, solid. But here's one of my other favorites, if I can do this.
You want the traffic to be liquid or gaseous if you manage.
Oh, I was just about to say ants. That was the one. Because I was at Georgia Tech talking to
Oh,
people
were you?
about ants.
This is such a cool. I'll just let you read it and watch it. Yeah, so this is where he talks about it as classical diffusion concepts, which we'll see a lot of in this class.
So many ants.
So you could try to model this by keeping track of each individual ant, but that would not be fun.
No.
This is the ants behaving like an ice sheet.
How does he get these ant balls together?
Whose job is that? That's an undergrad's job. This one, I don't know if you can tell, but this is a stationary hole, and the ants are just creeping up it, like a meniscus. So in this case, because they're flowing, you might have a density as a property, and then you might have a viscosity of as a property. You need to watch me here. And your viscosity might be changing through time and space as well. So a lot of the materials, so water has a pretty consistent viscosity. It stays, it varies so little that it's very rare that we need to actually keep track of the viscosity of water. It changes a little bit with temperature and a little bit if you add salt in there. It's so minor in the scale of most of what we do. Silly putty, however, will behave quite a bit differently if we warm it up just a little bit, just like honey does or anything like that. The viscosity of a material is something that we'll run into a lot in a lot of different ways. Viscosity can change with temperature. It can change with composition if you add something to it. It can change with the amount of stress that you apply to it. So there's some materials that will get softer when you apply more stress. There's some materials that will get harder when you apply more stress. These are all called non-Newtonian. All of that in general is a non-Newtonian material, because Newtonian is like water. It's got a constant viscosity, simple, keeps going. So we will talk about a lot of different types of viscous materials. But ants, yeah, that's one of the properties that we have. Any others you can come up with? Go on.
Syrup for pancakes.
Syrup for pancakes, yes. Syrup for pancakes. And that you heat it up and it totally changes its property after you cook it. It goes from being a liquid to a solid. You could totally model all of that. Okay. So any questions on that? Any so hopefully now you guys have an idea of what a continuum is. We've talked about how we're going to apply conservation of mass, momentum, and energy. We have to think about the material properties. And really what this comes down to is we're thinking about what can we do with these ideas that will help us estimate the strain distribution across Nepal in an earthquake, or whatever, figure out how much volume change that magma chamber is undergoing by measuring the surface deformation of our volcano, or what's changing. And so what we will be, the core, the fundamental basics that we'll be thinking about. So we've talked about mass, momentum, and you'll see each of these way more than you ever want to in terms of all written out. But these are our basic conservation principles. And then the properties of the material that we've been talking about, there's a couple of different ways, and this is all in the note, there's a couple of different ways that these are described. Constitutive relations, equations of state, like the ideal gas law, even though we're not going to be dealing with gas in this class so much because it's compressible and that just makes the equations more complicated. The ideal gas law is a very typical equation of state, or it's because it relates temperature and pressure for the gas and tells you what's happening with that gas, or what the behavior of that gas might be if you put a certain, because it relates the volume, the temperature, and the pressure. So in order to know what happens to it under a certain pressure, which is what we might be applying to it, you need to know what the ideal gas law is. Constitutive relations, these are kind of the same thing. They might have to do with the chemistry. This is where your viscosity will come in, and you'll see that. The ideal gas law is an example of this. In the world of electricity, this is relating current to voltage. So that's, again, it's a property of the material. A lot of this comes down to material properties. But in order to connect all of these, we have to think about what we've talked about are like the stress or the forces that we apply, or that somebody applies, or that are generated in this situation, and how that relates to our deformation or displacement, or strain. Those are the words that we use here. And within our stresses, and we'll talk a lot more about what stress is in a minute, the little Kleenex boxes. But within a stress, you can have what's called a body force. Anyone have an idea of what is a force that sort of that is applied to all parts of our body, our physical body at the same time?
Oh, gravity.
Gravity, right. Gravity is a great one. So it's very different than somebody pushing on you from the side, which is where you have a force that goes in on the edge, then is transmitted through your body. Gravity actually is applied to all of you at the same time. So with stresses, we can have a body force and we can have a surface force. And the surface force is that one where somebody comes and pushes you and knocks you over. And does anyone remember from their old physics classes, the relationship between a stress and a force? How does pressure come into it?
Air pressure is force over area.
Right. So force over an area is the stress, or in one dimension, we sometimes also call that the pressure. So force over an area. And in our continuum world, basically we're going to be thinking about forces applying to areas, but as we take those areas down to infinitely small areas, we can sort of conceptualize this quantity called stress that embodies both the force and the area, even though we give it one value. It embodies both the force and the area, because the area we've now has gone down to infinitely small size.
So the units don't stay stress, or the units?
The units do stay stress. Yeah. And yeah, so the units are units of stress, but now our area, which is still there, it's just an infinitely small area. And so it's not just a force anymore, because it has this area with it.
Wait, so what are the units of stress then?
Newton per meter squared.
Yeah.
Yeah, okay, so, yeah,
So
it
it's
is.
the same as
Yeah.
pressure. And so pressure is actually, the pressure that we think of is a special state of stress. And so we'll
Isn't it
get-
just the other side of the axis? I'm just thinking pressure would be, I was thinking positive, no. Positive
Oh.
numbers, and stress would be the negative numbers, because that's a pull.
No, well, stress and pressure can be both positive or negative.
Well, obviously it
Um,
depends on.
Yeah. So what pressure is basically a stress that's equal in all directions. So when you're down inside a swimming pool, you're getting pressure at you from all directions, right? And it's equal from all directions depending on how deep you are in the swimming pool. So it increases as you go deeper in the swimming pool, but it's still the same in every direction. It's applying to you. A stress is the generalized concept of that, which could be equal. So the stress could just be a pressure where it's equal on all sides, but the stress could also be that it's much, much stronger squeezing in this direction than in the other two directions. And so this thing with stress, though, if I say, well, I'm going to take a force, my finger is going to be a force, and I'm going to apply it to this area. If I just apply it like this, then my box goes racing off into space, right? Because there's nothing to counter that. So a stress actually is a force couplet. It's not just an individual force when we get it into this conceptual model, because an individual force can send something going off into nowhere. In this class, we might have things moving in space, but most of the time we're going to ignore that movement in space, because what we're interested in is how is this box going to get squished or stretched or deformed. And so the way you keep this box here but still have it deform is by having two forces, one on each side. And in this case, the area goes down to infinite, but when we get into 3 dimensions, our entire box is going to go down and become infinitely small. So this box is sort of like the force over the area, and the area goes infinitely small. In reality, the stress, the best way to picture that is a box like this, but then the box gets infinitely small. And so we have our force couplet here that's causing this to get squished inward. We could do the same thing with even though this isn't a box, by squeezing the silly putty, there's a bunch of little tiny boxes inside there that are the stress at each point inside this body.
Yeah, the PowerPoint.
So if we have a body like this is our silly putty. We squeeze it here and squeeze it here. We can visualize this as a bunch of boxes that each have that force couplet on them from this bigger force on the sides. And in the continuum concept, these boxes basically shrink down and are infinitely small, and we kind of ignore that they take up space. So they become a point, and that this would be the stress, which we often use as sigma, at this position, x, y, z, within our body. In this one, sigma, x, y, z. It might be that sigma is the same everywhere within our body. But you could imagine, say we actually had two slightly different materials there, then, or we have a little bit of extra stress on one side, or because of the way that it's shaped funny, if this starts out shaped funny, then you might have stress that varies through your body. It won't necessarily be constant through the whole body. If you have a very simplified, straightforward stress, you apply the same force on either side. So this is now a real Kleenex box. Well, a solid box. If you have the exact same material within there, the geometry is simple, you apply the same force on either side, then the force all the way through there would have to be distributed the same. So you would have the same stress throughout this whole body if everything otherwise is the same. But if things aren't quite the same, then you can have stress changing with space within your body, which is how you get your ultimate deformation maps. At the end, you deform your body, and now you have your new body. And here, so in our world, this is different than what a lot of geologists do. Positive is outward, and negative is inward. Geologists love to talk about compressive stress as being positive, so it's just a convention, but if you read a paper and they talk about compressive stresses as being positive, then you just have to rearrange it in your head. This version that we use is more standard in engineering and physics and geodynamics. It's just the geologists that like to have, mostly just because they're always dealing with compressive stress in the earth. So if you're always dealing with stress in one direction, there's nothing wrong with the other convention. It's just mathematically it's a lot easier if things getting bigger is a positive measurement and things getting smaller is a negative measurement. This box, though, I'm going to keep getting, we have 10 minutes left. So here, you guys should each take a box, please.
Oh, sorry. Thank you.
So what we were just talking about was this force couplet where I'm pushing in on both sides of here. But as you'll see, there are 9 different sides to this box.
Wait. 6?
1, 2, 3, 4, 5, 6. All right, 6 different sides to the box. A tensor has 9 components. That's why.
Yeah, there's something I'm missing.
So we have this one, but then we can also have this one, and we can also have this one. So right there, that's 3 different stresses that are applied to the same infinitely small box. In the pressure situation inside the swimming pool, those 3 are all identical, and there's nothing else going on. You're just squeezing it the same from all directions. we need a way to be able to describe those 3 different ones and make sure we know which ones we're talking about. Like if I give you that box and I tell you what the X, Y, and Z or the 1, 2, and 3 coordinate system is, I should be able to tell you what stress I'm talking about, and you should know immediately relative to the coordinate system if I'm talking about this one, or this one. So we have a convention for how we do that. What is the other way we can apply a force to this box?
Shear
Yeah, do you want to show that with your...
on the face, and then you. I don't want to destroy the box. But left hand
So
goes
what do you-
up, right hand goes down while applying force inward.
Good. And if you do that, right hand, what happens to your box?
It'll deform into a polygon.
And
The left side will go up. Rotate.
if you
Is that
just
what you're
have,
looking
yeah, so it might deform, but if you just have those 2,
for? It'll just rotate.
it's going to start to rotate. So what do you need to stop it from rotating?
Compression.
No,
Different speed, different rate of change.
a different rate of change. You guys are
Suppose
good
one
at those.
one of your hand was
So
faster.
compression will squeeze it while you're rotating it. A different rate of speed with one hand versus the other, is that what you said? Then you wouldn't have, so they need to match. They need to be, but what's the other force that I could apply to stop this from happening?
Friction.
On
You stick it
Friction.
to you.
stick it to you.
Stick it to your hand.
Maybe a
then you're good.
solid bottom underneath, so you can't like.
These are
Well,
all good
that's how
ideas.
it is.
Can you put your hand on there in some way, not on top of mine, that would stop it from rotating? Okay, that one. How about both hands? What are you doing?
Adding another force, so on top and bottom.
And the top and bottom, in which direction are you pushing? Are you pushing
Down.
pulling towards yourself, or are you pushing?
I'm pushing down. I guess if we're doing like this, it's downwards and upwards.
Downwards and upwards.
Is it applying
Relieve
another?
the downward. Don't push down. Just
Okay.
use friction in your hands.
I guess side to side then.
So it's another
Yeah,
shear.
so adding that second shear will stop it from rotating. So we need that shear couple. So just like the force couple, we have to have both forces to get it to not fly off to infinity. We actually need to have both shearing forces to stop it from spinning. So so you need to have both to keep it from spinning. And then you can figure out how it's deforming once you've got it stopped spinning. So you balance the forces enough to stop it from spinning. Then what's left over, the resultant force stress combination, will allow it to deform. So basically the way we can come up with a convention to describe this. So we have our force, and this is our area, right? So our stress is a force over the area. This force, if we give ourselves 1, 2, remember the axes convention, the right hand convention, 1, 2, 3. So our third axis comes out of the page.
Mm-hmm.
It's a good one to always remember. I have to sit there and do it. Yeah, there's the other one, isn't there? It's like the left hand version. Or is it the right? Is it the right hand? I always go 1, 2, and the pen goes flying off. So here I can tell you that there's a force that's in the negative x2 direction, right? Because this is our 2, and it's a downward force in the negative x2 direction, or just in the x2 direction, because actually needs to
Oh,
have
all
its-
these are X's? Well,
Yeah, or you could
okay.
use, yeah.
No, just whatever.
X1,
yeah.
X2, X3.
Okay.
We do use 1, 2, and 3 for axes more than X, Y, and Z because X, Y, and Z we use for the spatial position in space. 1, 2, and 3 we use for the local description of what's happening at that location in space. So we have a force that's in the X2 direction. How would we describe this area in terms of its direction?
Normal.
The normal. What's the normal to our area A?
Positive x2.
Yeah, so it's in the X2 direction too. So what I just drew here is some force F that's in the X2 direction and being applied to an X2 face. Mm-hmm. Do you have a question?
Yeah. Are you sure about the 1, 2, and 3 sides of the box? Because I remember I was reading it this morning and it was different.
Isn't it 1, 2, 3 with
Like
your
one
right
is-
hand?
Yeah, that's
One is X positive and then Y is the second, and then the third one is the Z positive, if I remember it correctly.
Oh. Yeah, so you can draw them
Yeah, this.
1, 2, and 3 if you want.
that's the same. Turn and
Or is
it is the
So
same.
1, 2, 3.
yeah.
As long as you define your coordinate system,
Okay.
you can use whatever you want for that situation. And it is very common that we use 3 as the up direction because that's we think of as the Z direction, but it just depends on whatever you're comfortable with. So yeah, these are actually equal, but I have to define it so that I can tell you to go to the force that's on the in the X2 direction and on the X2 face. And then you'll say, yeah, that's a normal force that looks like this, or that's a normal stress that looks like this. If I put this shearing force here, so this will be our F2 if this is F1. What's the direction of this new force we have? It's a shearing force.
Next two.
Right, it's also in the X2 direction. And what's the face, the normal to the face that it's being applied to?
Minus x1.
Positive.
Yeah,
Oh,
the X1
okay.
face. And because you do have to keep track of that, because these are always in couples, we have a negative force on this face and a positive force on this face. The normals are in the opposite direction, so the negative signs end up canceling out, but you do have to be careful because overall a negative stress does mean compressive. A positive stress means expanding. Negative and positive in terms of shearing does depend on your coordinate system that you've figured out. So
How come F2 is in the X1 direction? Shouldn't it be?
which direction is F2 in?
Shouldn't it be going up in X2?
Yeah, it's the direction of the force is in the X2 direction. But the area that it's associated with
Oh, I see.
is in
Okay.
the X1 direction. So, are you guys sensing a pattern here that all of these forces, I could draw this one or this one? Could you tell me which direction and then which face it's being applied to? So this one is in the X1 direction, but it's on the X3 face. This one is in the X2 direction, but it's also on the X3 face. Maybe this one's a lot bigger than this one. So it might have a bigger magnitude, but the directions are still defined there. what that means is that every component of stress here has a magnitude, so an amount, and it has two directions associated with it. So you always need to know the magnitude and the two directions in order to be able to define that component of stress.
Wait, I'm not following. So we said each force had one direction. So what are you saying?
The force has one direction, but the area, because remember stress
Oh, to
is
say-
a force over an area.
Right.
So you have one direction associated with the force
Mhm.
and one direction associated with the area.
Mhm.
And so a stress will always have a direction associated with the force and a direction associated with the area. So it will
Right.
always have two directions.
But you said you need two directions.
You always need two directions to define a stress.
But here you show that you can. Oh, because an area is two directions. Oh, I'm not.
Both of those are directions. So the in, if it's it's going in a direction. That means one thing, but it's also on a certain
Mhm.
side of it, like the shear.
I see.
So
So
you
in-
have to know the in and the on.
Yeah, the area, the side of the box that we're talking about
I see.
is defined by the normal to it,
Right.
which is always perpendicular to it. So we can, an area always has a normal that defines it. The
Got it.
force always has a direction that defines it.
It's like grammar. Area is a subject. I get it.
Yeah. So, how many directions are associated with a vector normally? How many directions are associated with a scalar value?
None.
None, right. So a scalar value is a volume or like an amount, but it has no direction associated with it. A vector,
One.
one direction, right. It's got a magnitude in one direction. Here we have a magnitude in two directions, and we always need a magnitude in two directions to describe stress, which means that it's not a vector and it's not a scalar, it's a tensor, which is where, oops. Oops, 4. 2, 1. I'm just using F as the magnitude of that. So this force is being applied in the one direction on the surface area of our box that's also has the normal in the one direction. This is what I always forget. Because it ends up kind of not mattering in the end. But I do like to make sure it's. So the first number, when we write these out, the first number is the normal to the area. It doesn't end up mattering very much in the end, but it's just good to think about it that way. So this force is applied onto the 3 side, which if we have 1, 2, and 3, that would be this side, but it's pointing in the one direction. So we're on this surface pointing in the one direction, which means that it has to be a shear force, because the only way you can have a force that's pointing in one direction on a surface that's another direction is for it to be a shear force. So basically, these describe the different forces you can have on your box. And this, because each one has to have a magnitude and 2 directions, we can start to write it out this way. And because we live in a 3-dimensional world, I'm just going to put IJ we always go 1, 2, 3. If we lived in a 4-dimensional world, we'd have 4-dimensional. But thankfully we only live in a 3-dimensional world. So this is what a tensor is. And the important thing to note is this is not just a simple 3x3 matrix. Because the tensor is, it is a type of matrix, but it's a special matrix that has this relationship of that it's a magnitude in 2 directions. And so it will have special properties, and what we'll talk about on Thursday is that to keep it from spinning, we actually need to have these be equal and opposite. And these need to be equal and opposite, and these need to be equal. So we will basically on Thursday we'll move from this to getting into some more of the mathematical foundation for how you work with tensors. I will try to put up the assignment today or tomorrow, but you probably won't want to dig into it until at least Thursday when it'll start to make sense. So, sorry, I didn't realize. I went a little bit over.
When will the assignment be due?
It's usually due a week after the end of a unit. So it'll be due 2 weeks from Thursday or so.
Okay.